Hi class, I'm here to talk to you a little bit about numerical time or absolute time. For this part of the Geologic Time Lab, you're going to be working with half-lives, parents, and daughter uh, numbers, really. And we'll talk about what those units are, and then ratios. And you'll be using your ratios to evaluate the number of half-lives that have elapsed, and then apply that to calculating numerical or quantitative ages for the parts of the lab that have been assigned. The first part of the lab is to go ahead and fill out this table. And so what I'll do is I'll talk to you through filling out the first part of it, all from parents all the way over to ratios. Well, and then we'll then do a couple problems together, and I'll leave you to fill this table out and then to wrap up the plot that is below it on your own as well. Okay, so I'll go ahead and switch over to my pen tool here. The idea here is we need to start somewhere, and at 0 half-lives you're going to have all of the parents in the system, and you're going to have none of the daughters because the clock hasn't started yet at 0 half-lives. In this case, I'm recommending you start with 100 parents. All right, this could be 100 atoms, 100 grams. All of these are applicable. So we'll start with 100 here. Okay, this could also be a percentage. We're going to start with 0 daughter atoms here at 0 half-lives because the clock hasn't started. Okay, parent-daughter ratio does not matter, and this ratio is also not relevant. Now, after 1 half-life, we're going to cut this parent in half. It now becomes 50. 50 atoms, 50 grams, 50%. Okay, that half gets added to 0, and we end up with 50 here. Come over to the right, we now have daughters divided by parents. So this is daughters divided by parents. We get a ratio of 1. Okay, now 50, the parents divided into itself, we get a value here, kind of like a ratio like this, of 1 to 1. Let's cut this 50 in half. We're going to go to the next half-life, the second half-life. Now we're at 25 parents. We are going to add the 25 here. Over here, we're now at 75 daughters. We're going to be at a daughter-parent ratio that is going to be 3. Okay? So the ratio over here is now going to be 1. 25 into 25 is 1, and 25 into 75 is 3. It's going to be 1 to 3. Okay? Cut this 25 in half one more time, and we're down to 12.5. Okay? That 12.5 that was lost here is added over here, okay? And it's going to give us 87, okay? 87.5, okay? 12.5 divided into 87.5, that's this ratio here, is going to give us 15. And our parent-daughter ratio then is going to be 1 to 15. Okay. So you can take this all the way down, splitting this parent-daughter ratio in half, adding the stuff that you subtracted. In this case, we're down to about 6.25. You'd add it over here to 87.5 and put that in this box. And then move to the right, calculate your daughter-parent ratio, and then your ratio of really it turns out to be of parents to daughters instead of daughters to parents. Okay. The next step then is to apply this information to making calculations regarding half-life. And that's where this table comes into play. On the left, we have the parent. On the right, we have the daughter. And so for different questions in this particular example, you're going to start with, let's say, carbon-14. Let's go over here. Carbon-14 is our parent. It's going to decay to nitrogen-14, which is our daughter. And we're asking a question about the age of a bone. Okay? In this case, we know we have 87 grams of nitrogen-14. That's the daughter. So there's been a fair amount of decay. And we know we have 12.5 grams of carbon-14. If we jump over to the table we just filled out, okay, you just filled it out, where do we have a parent-daughter ratio that looks like that? 12.5 to 87.5? That's 3 half-lives. So down here we're going to put 3 HL. I'm just putting HL for half-lives. Okay, I'm simplifying this a little bit. Okay, and now we need to multiply it by the years per half-life, and that's written here, half-life approximate in years, days. So here for carbon-14, it's 5,730 years per half-life, right? What do we get out of this when we multiply? Well, half-life cancels with half-life, and we end up with a value of 17,190 years. All right, so that's your answer for the age of the bone. We have another problem down here, which is a little bit different. It's got, again, done in grams. You may see ratios of parent-daughter ratios here instead, but in any case, you're going to go back to the original table that you just filled out, the first table on page 104, where you essentially fill out the parent-daughter ratios for each of the sort of subsequent half-lives. Come down here, we've got the xenon 31. Let's find it up here in this table, xenon 31. Oh, here it is. It's the daughter atom. Okay, and we've got our parent over here, iodine 131, which is right there. So parent to daughter. How many half-lives have elapsed? Well, once you fill out that table, you're going to get down to the point where you can answer this. I will tell you that 1.5 parents in terms of grams and 98.4357 grams, that's going to give you a half-life of 6. Okay, I'm getting that from the table that I've completed. So let's say we have 6 HL times what? Well, we're going to come up here and say, well, the half-life is 8 days, so times 8 days per half-life, okay, which is equal to 48 days. So this sediment sample, okay, that we took from the field is 48 days old. All right, so in the future, you're always going to kind of refer back to the original table on page 104 that you filled out completely, and you may find that you end up with ratios being given to you. You may get grams, you may get percentages, but the basic idea is that all of them can be used to determine the number of half-lives. And then it's just going to be half-lives times the time per half-life, okay? And that's going to come from here on this table that's right in front of you.